And thank you, Stefan, again for agreeing to continue your tutorial on dynamic low-rank approximation. I think we can start whenever you feel like. My clock says 12:05.
All right. So we're going to continue on with this kind of mini primer into dynamic low-rank approximation. So last week we talked more about the theoretical underpinnings of dynamical low-rank approximation, how it's defined, determining the properties and approximation properties and how they work. And this week is going to be more about how you actually computationally implement dynamic low-rank. And to talk about and to show an example of kind of what the machinery can do for you. Okay. So just a quick recap of last week. So the goal is that given some matrix valued differential equation in time, so y is here as a matrix that's, let's say, m by n, and it satisfies some dE dynamical system, y dot equals f of y. The goal is to find some rank R matrix U that's approximately close to Y. And U also evolves in time as well. There are several ways to do this. Dynamical low-rank approximation takes the Riemannian approach and says, okay, I'm going to look for an approximation matrix U that's rank R in this manifold, rank R manifold, such that the dynamics of U are the dynamics of the traditional system and projected onto the manifold. So U dot is going to be the equation f of U, but we have to project back onto the tangent space continuously in time. And this will keep the solution rank R for all time. But now that you know your solution is rank R, your dynamical low-rank solution is rank R, you can give it an ansatz of CS times D transpose, where C and D are both orthogonal. And then you can show that this system called the equations of motion, that is an update for the factors C, S, and D hold. So we talked about this, but we also saw that the equations of motion above, you can't numerically time step them unless you take the time step sufficiently smaller than the smallest singular value of the matrix. And in the case of, and this is usually much lower than 1, and in the case of over approximation, where you want to make sure you have low consistency error of your rank approximation, this gives you very small time steps to be practical. So we're going to focus on what are called integrators, or you can think of it as numerical time stepping schemes that allows you to approximate the dynamic low-rank solution in time. So for this kind of set of slides, we're going to assume that you have the solution as a rank R function, rank R matrix, sorry, at some time t0. Given by C0, S0, and D0. And we're going to build some new approximation C1, S1, D1 at a time T1, which is T0 plus some small times delta T. So again, the way to think about these integrators is to think of the rank R manifold as a ruled surface. And this is just an example of essentially a cylinder that's attached by strings, and you rotate, you twist counterclockwise on one end of the cylinder and clockwise on the other, and you'll create a small curvature here around the middle. But it's
Can I ask a quick
composed
question?
of straight lines. Sorry?
Can I ask a quick question?
Sure.
If you go back to the previous slide, this is a very high level question. So you have a way, this dynamic low rank approximation is a way to do the projection, right? But suppose, so your U dot, U will be projected. Suppose I have another way to do the projection, or in general model reduction, right? You get this U projected. You can still use your second step, this step of integrate time stepping, right? I'm thinking these two decoupled components.
Yeah, so the numerical integrators are based on dynamic low rank, but there's no inherent way you could use them in other contexts. Yes, you have that.
Yeah.
As we'll see here.
Can I ask one more? Sorry, this is maybe a reminder of the previous one. So the claim is what, that the entire trajectory UT is close to YT, but UT happens to be the whole thing, every pointwise is rank R? What exactly is the Like how should I interpret the approximation? Find UT approximately YT.
Yeah, so you assume that your solution Y is close to something in rank R, and your goal is to find a rank R matrix that is close to it. So yeah, you're assuming that your Y is approximately low rank, right? And your goal is mainly to, I mean, even if Y was completely low rank, you would still want to find a representation that gave you that, right?
So I guess my question is the other way around. So if YT is not low rank, am I going to find UT that minimizes the distance between the trajectories of UT versus YT, or what is actually going to be found?
So you'll find something that's approximately close to the best rank R approximation you can get, right? So you'll always have a bound error of your rank approximation error, but the dynamical low rank will get you what's called quasi-optimal in a sense, right? It's a constant away from your best approximation.
Okay, thanks.
Okay, so the main thing is that while this rank R manifold is very curved, right, has high curvature, which is what induces the small scaling in the time step. If you revolve the equations of motion, you essentially have to take very small time steps to resolve this curvature, and that curvature is dependent on the reciprocal of the smallest singular value. It's made up of a bunch of straight lines, and in our context, these straight lines are just linear subspaces of the manifold, and we want to essentially traverse this manifold by staying on straight lines and not trying to resolve the curvature. In the literature, there are two main integrators that have done this, and there are variations of each of these. The first one we'll talk about is the projector splitting integrator. This was the first one to be developed. And the second one, which is the more popular one used today, is what's called the basis update in Galerkin, or the bug integrator. Okay, so all of these integrators use essentially some form of operator splitting. So what the projector splitting integrator does is essentially, it says that I can algebraically represent the tangents, the projection onto the tangent space. So recall last time we talked about how you could take the tangent space, and knowing your decomposition of the matrix, you could give an explicit representation of the tangent space. Well, if you have that, you can also have an explicit representation of the projection operator. And it's given by a sum of three components. You essentially project onto the right range, you project onto the left range, and you subtract off the projection onto both the left and right ranges. And you can show that algebraically this is the tangent space approximation. And what the projector splitting technique says, okay, I'm going to do operator splitting using this sum of three things I can easily work with. And for those who don't know, operator splitting essentially says, okay, if I want to take the exponential of a sum of operators, if they don't commute, then I can't just take each one by one. Then I essentially say, okay, I can just do that, and I'm going to incur some error. And that error I'm going to incur is the order of the time step. So this will be essentially a first order method regardless. So I essentially want to have my tangent projection operators, the sum of three operators, and I'm essentially going to say, okay, I'm going to apply them each sequentially now, instead of trying to do it all at the same time. So if you do that, then you essentially have split your one ODE into three sub-ODEs. You're going to have your first ODE, which is going to do P1, your second ODE, which is going to be this P2, and then your third ODE is only going to advance P3. And then at the end, essentially, the result of the U3 update will then give you something hopefully close to U at T1. Okay, so we're first going to focus on that first ODE update, which is given by this right here. So essentially projecting onto the right range.
Quick question, is the number of terms fixed in this situation? Why is it cannot be more than 3 terms?
So that's because the projection operator here is 3 terms. So if you had a higher order tensor, there would be more.
Yeah.
Exactly.
You could have more. Yeah. Okay.
Yeah. But in a matrix case, this will be fixed at 3. Okay. So we're going to look at solving this ODE. This looks very complicated, but it's not that bad if you do some analysis on it. So essentially, when you project a matrix onto the right-hand range of U1, you can show that always lives in the tangent space of U1. So that essentially automatically guarantees that U1 is rank R for all time. And since we know it's rank R for one all time, we can give it an ansatz. So we're going to give it an ansatz of a matrix K times a matrix D, where D is n by R and orthonormal, and K is just a generic n by R matrix. So this represents the degrees of freedom for this problem. Then essentially, if I plug this ansatz into the ODE, I get a product rule for U, that it's K times D. And on the left-hand side, since D1 is orthonormal, the projector operator is represented by D1 times D1 transpose. And essentially, I'm looking for a solution to this equation. And you can easily find one by saying, okay, if I set D1 to be constant in time, then D1 prime is 0, and that knocks out this equation right here. And now, or knocks out this term, sorry, right here. And now that D1 is constant, I can then just solve the residual component by multiplying by D1, and you can get an equation that looks like this. So essentially, when you set the initial conditions as your initial decomposition, C0, S0 times D0, since D1 is constant, it doesn't change away from D0, its initial condition. And essentially that means that D1 is D0 for all time. And that allows me to plug this in here. And then K1 is then evolved by these dynamics, where the initial condition is just the C0 times S0, the other two terms of the initial condition. And then I can evolve K1 essentially forward in time. And now, since this equation is just a linear projection onto the dynamics of D0 essentially, so there is no curvature here to resolve. So I can time step as I wish, using any integrator I really can use, and the time step is only restricted by the problem itself, F, not the curvature. I can then essentially solve this ODE for K1. And now that I can do this from T0 up to some time T1, and that gives me K of T1, and then I can do a QR factorization to recover a basis C1 and the coefficients S1. It doesn't matter necessarily. There are obviously multiple C1s and S1s that guarantee this from a QR. You can choose any of them. It doesn't matter. This is independent of the choice you make. And then we set U1 then to be C1 times S1 times D0, since we didn't change D. So this step is often called the K step, right? So you fix D and you're updating it on the straight line dynamics of the manifold of the K step of C times S.
So sorry, can you give us some intuition for why the choice of D1 doesn't matter? It would seem like it should matter in some sense, like in some fashion, but it seems like it drops out somehow.
So essentially, you just want a solution to this equation, and one can be achieved by just setting D1 prime equal to 0. So you're making some consistency here, right? Because you're not allowing yourself to evolve D in this case. So you are making some consistency here in your time stepping, but this allows you to then go on a straight line in the manifold and not hit the curvature essentially. So you're trading consistency error for stability error in that case.
Okay.
And D1's just but
are there, like,
D gives you the best representation.
Presumably there would be some Ds that are really bad choices, or is that not the case?
What do you mean here? The choice of D is fixed by your initial condition here, right? You're given this decomposition here.
Oh, we're given, okay.
Yeah, we're given C0, S0,
okay,
D,
got it.
and you're fixing D and evolving this. Now,
Okay.
your choice here, C1, S1, those can be changed. Those can be, there are multiple ways to get a C1 orthonormal and S1 that gives you this, right? That doesn't matter. It just choose any of those, we're fine. Because essentially the method is robust to how you choose these C1 and S1 here, but the Ds are fine.
Okay, I see now.
Okay, so the second term is this projection onto the left and right-handed ranges of the matrix. We're essentially just gonna play the same game, but in this time you can show that the solution still is rank R, and it's going to be given by the span of C and D for some C2 and D2. And you can plug everything in, and you can essentially say that, okay, my choice here is I'm going to make the C's and D's constant in time, and I'm just going to evolve the S by projecting onto the span of C and D. So remember, the previous output was C1 times S1 times D0 down here. We're going to use that as the input into our next substep here. So we choose C2 to be C1 for all time and D2 to be D0 for all time. And then we're going to evolve S2 via the dynamics of projecting the solution onto the range of essentially C1 and D0 with the initial condition of S1. So you evolve that in S, and that will give you then an updated S. So we've essentially updated the C, we've updated the S to this S2. This is called the S step. And then the last step is going to be evolving the D step. And that's going to be done by the U3 equation. Where essentially now, instead of in the first step, we fixed D and evolved C through the K step. In this case, we're going to fix C. That was, sorry, we're gonna look at a solution that essentially evolves an orthonormal C and a variable L, which L essentially here is S times D transpose. Sorry, S times D transpose. And you can show that, well, C is really constant in time, so it's just going to be the C1 you had from before, and you're going to update the L via a similar type of equation where you fix the C this time because it's constant in time. So before, in the first step, we fixed D and evolved the dynamics, then we went backwards to get S, and now we're going to go forwards finally to get D. So when you evolve L to time T1, you get a D3 times an S3 transpose. So then that finally gives you a solution as C1 times S3 times D3, and that will be your actual approximation at the time step T1. So this step is called the L step, and you'll often hear this algorithm called the KSL algorithm. That is the K step, the S step, and then the L step. So we've kind of subdivided this problem into, we've taken the problem and subdivided into 3 subproblems, each of which have time step restrictions that aren't dependent on the curvature of the manifold, with the cost of some consistency error. I know that was a lot. It's very technical, but I'm trying to give you a higher level overview with as little algebra as possible what's going on. But essentially, you solve 3 ODEs given in sequence. Is there a question?
Can I ask a different question, which is like the way you sort of explain this at the end, it sounds a lot like, say, a block coordinate descent algorithm, where you sort of solve for each of the factors independently. Are there relationships known between these splitting methods and block coordinate descent, or is that just sort of?
Yes, there are. If you look at a problem that's trying to just minimize some cost function, and you look at like a gradient flow to the minimum, these algorithms can be like, you can think of these almost like an ALS type of formulation or a block gradient descent exactly. In this case, though, we're not trying to reach some minimizer, and doesn't matter the path to get there, right? As long as we get there. And this time we're trying to evolve dynamics on some manifold. But yes, in the case where you're looking at some, maybe let's say long range equilibrium given by the times by the ODE, you can think of it in that light exactly.
Okay, thanks.
Okay. So we can solve this as a sequence of ODEs. And again, the important part is that we don't require inverting S. We avoid the curvature of the manifold. So our time step is purely based on the time step of the F. And I mean this, like and I work in the world of PDEs, your F is going to have some time stepping based on discretization and some like CFL condition. And that's what you have to respect in these time stepping schemes, not the curvature of the manifold. And again, these are written out in terms of the substeps or ODEs. They're reduced ODEs, but they're ODEs nonetheless. So you can then plug in your favorite time stepping scheme, either RK or multi-step or whatever you want. Symplectic, doesn't matter. Can be applied to each of the substeps. You can show that the local truncation error is order delta t plus epsilon. So epsilon is the rank approximation error. The equations in motion are, order epsilon essentially. That's their error. So you essentially induce a first order time stepping error in order to resolve the dynamics stably. You can also do higher order projector
I
splitting,
have a
operator
question
splitting.
here.
Yes, go ahead.
So delta t, the relation of delta t and epsilon, I think you said delta t needs to be a lot smaller than epsilon, right?
So no, these are decoupled now.
Oh,
So if you
okay,
were to evolve the equations of motion, if you were to evolve if you were to involve these equations, you do have a time step restriction essentially based on the smallest singular value. But
That's right. Yeah.
But in the projector splitting, there is no, this is purely just a consistency error term. There is no restriction on delta t via the singular values of S. We've gotten rid of that.
All right. So because it's decoupled.
Yeah, essentially, you're right. Essentially, the projector splitting essentially decouples the tangent space to the F, and that is what induces the curvature dynamics that that give you the unstable evaluation
Okay.
for low steps.
So that's very favorable. This.
Yes. So the equations of motion are almost never used without some sort of regularization. It's
Okay.
way too unstable. While this is not used as much now. I'll explain why in a second. But you'll still see papers that use this. And if you don't, there is a caveat to this, which I'm about to explain. But if you don't have that caveat, this is a perfectly valuable method. Another advantage of this method is that you can do higher order operator splittings. So the one we did here is called Lee-Trotter. It's the simplest, but you can do higher order what are called strang splittings. That's a popular second order splitting. But you can't guarantee stability of that like you can in the Lee-Trotter case. Let me skip this point right here. I also want to say that this has been extended to a work on tensor trains. You can look up this sign-on paper for more reference, but this kind of carries natural to the tensor train format, to where as you move down your train, you're doing a basis update and then a coefficient and then a basis update and then a coefficient as you move along the train. So you'll have in basis coefficient updates you'll have D basis updates for your D vector or tensors in the train, and then you'll have D-1 coefficient updates in backwards in between the trains. But I will say that one of the problems of this method and why it's not used much anymore, it's still used, it's not as popular anymore, is because of this S step right here. And the main part is that you're going backwards in time. You have a negative S, a negative here, while your other evaluations are going forward in time. And the problem is that if you look at this in the context of PDEs, some equations don't have aren't time reversible. So for example, if you want to try to do diffusion on this, which very often has low rank structures, you couldn't do this scheme numerically without it essentially blowing up in the S step, because diffusion is ill-posed going backwards. So if you don't have for example, if you're doing some convergence to equilibrium or something, or you have a problem that is time reversible and you have a numerical scheme that respects that, this is a perfectly valid algorithm, and it's still useful for that. But it's limited in its respect because of this backwards in time operator. So to to develop an integrator to solve this issue, one was developed relatively recently, back in maybe just 4 years ago or so when it was first introduced. And this is called the basis update in Galerkin, or the bug integrator. Originally, it was called the unconventional integrator, but it's probably not good branding to call your method unconventional. So they're trying to do a renaming tour here. So it's called now the bug integrator. And this is just a way of time stepping that has the similar properties to the projector splitting integrator, but doesn't have the backwards in time solve. And it still uses the KLS step as before, the same substeps as the integrator in a sense. So there's another way you can derive the K step from the projector splitting integrator, and this is essentially the methodology that the bug integrator uses. So recall that before we had an equation for the K step that looked like this. And again, there's no S inverse, there's no curvature of the manifold built into this. And you can get this from an approximation of the equations of motion. So recall, these are the equations of motion that I had before written down. If I do some algebra on this C dot term here, so first off, if I move the S over and look at C dot times S, I get just this, and I can essentially can break up and distribute across the negative here, and I get these two terms. And if I look closely at the term highlighted, that's exactly S dot from above. So I can essentially write that as C times S dot. And now I have a C dot S, and I have a CS dot. That's a product rule. If I let K equal C times S, and I can essentially rewrite the equations of motion in terms of K given by two equations right now. Now, I haven't done it. I've just done some algebraic trickery, right? I haven't actually done anything. and I can't evolve. These still have the, you know, whole curvature constraints built in, right? Because even though this looks very nice, I still haven't decoupled completely because D involves C on its own. So I haven't decoupled D from K. And I still can't use this on its own. But what I can do is I can say, okay, I'm going to make an approximation by essentially approximating the D solve by just setting D dot equal to 0, kind of like what I did in the projector splitting algorithm. So I'm going to take this top equation system here, which is very messy and has the time step constraints of the curvature. And I'm going to evolve it by this approximate system that doesn't have the time step constraints of the curvature, because now that D dot is 0, D is constant in time, and now I can update the K step just as I did before. And I can use the same initial conditions as I did in the K step of the projector splitting. That is setting, if you have an initial condition, C0, S0, D0, I let D equal D0 and K at D0 be C0, S0. And I can do the exact same thing as the K step and evolve it forward in time. Now, before in the projector splitting integrator, you cared what the S was because you used that as your next initial condition to go backwards in time in the S step. But in the bug case, we actually don't care what we only care about the basis, the C basis. So we actually don't care about the coefficients it gives you at T1, because we're not going to actually use them. So we're just going to do some QR to orthonormalize the basis of K, the span of K, and then we're just going to chuck out the coefficients. We don't actually care about them. And the reason we don't care about them is because we're going to do the exact same process for the L step. So as you saw in the projector splitting, we went K, S, L. And this time we're going to do K, and then we're going to do L. And we're going to do L as if we're starting at the initial condition. So you can show, just as I did before with the K step, that the L step you can represent like this, where now I use C0 of my initial condition as the fixed basis for the L step. And I'm going to use DS transpose as the initial condition for my L. I'm going to evolve K and L almost pretty much in parallel at the same time. And that will give me a basis C1 and D1 at the next time step, T1. So this is where the basis update comes in of the bug. So we update both bases, K and L. And this can be done in parallel if you want. And then we're going to evaluate the S coefficients. The S step is done by just projecting onto the span of C1 and D1. So before, in the projector splitting, we had a negative sign here because we were going backwards in time for the Lee-Trotter splitting. But in this case, we're updating C and D at the same time in parallel, and then we're going to update S after the fact with the new basis created by the K and the L steps. Where we take the initial condition, the CSD, we project it onto the new basis, C1 and D1, and then evolve the R by R system forward. And that gives us the new, and so S1 is just S evolved forward, and then I get a new system, C times S times D, all with ones on them. And the advantage of this is S doesn't go backwards in time anymore, right? So now for diffusion or something, or almost all numerical stability comes from some sort of dissipation. So you can essentially maintain the stability of your method in terms of physical space with this sort of scheme. And it has the same truncation error as at least asymptotically as the projector splitting integrator. And disadvantage of it is it contains a larger error constant. And that's because you're not following the dynamics as well as the projector splitting integrator going forward, back and forward. You're going forward too, and then doing a giant projection of the initial condition. And that can presume some error, especially if you take longer time steps. The error constant can get much larger. But I will say, because of this fact, you don't have to evolve the coefficients in backwards in time, and you don't have to evaluate your ODE backwards in time. This has become much more popular in recent works. And you can think of this method as kind of like, in terms of tensor factorizations, you can think of Tucker as a natural extension of this method, right? So if you had a Tucker decomposition of a tensor, you can think of the basis update as updating each of your basis matrices, and then the S step is evolving your core, right? So you'd have D basis updates for each mode of your tensor, and then you have a final S step of the core at the very end. So this is extended to both Tucker, but there's also been a recent work that extended this to hierarchical Tucker as well. If you feel free to look at that paper if you want that. I don't know all the specific details, but they do a tree tensor format and apply this algorithm to that. So I just kind of want to tell you how this algorithm would look, how this works kind of algorithmically. So just as a simple example, again, each of the substeps, you can use whatever integrator you wish. So let's assume we'll do forward Euler. So just a simple first order Taylor expansion, essentially, of the time derivative with this bug integrator. And essentially you start with a C0, S0, and D0, and you end up with a C1, S1, and D1. So again, your first step is the K step. And essentially that looks like your initial U0 times f of U0, but you're projecting onto the D basis. So you put a D right here, and you just evaluate f times D0, put a delta T on it, and that gives you your K1. So that was your K step. Then you just do a QR of your K and throw out the coefficients, the R coefficients, doesn't matter. You get left with your basis C1. You can then, at the same time, if you wish, do the L step, where you evaluate f times C0 this time, and add that to DS, your initial condition projected onto the C basis, and that gives you L. And you can do a QR there. Next, you just project onto the new basis created by C1 and D1, and that's given by a matrix multiplication right here. And then you evaluate the S step in R by R by taking F and multiplying it by D1 and C1. And that gives you S1. So while there's a lot of, projector splitting, there's a lot of operator splitting and stuff going on, algorithmically, it's pretty simple in the sense to do if you have QRs and you see later SVDs, and you have all this machinery for doing, tensor operations, it kind of fits naturally in that framework. But lastly, I want to talk about also, how do you evaluate this F, right? I've kind of hidden this up until now, right? Mainly, if you notice in each of these algorithms and anywhere you see dynamic low rank, F is never treated on its own. Never have F of U, because even if it's not written that way, even though you might expect F of U to be low rank, it can be written in the way that it's essentially full rank. You can only evaluate it by evaluating U pointwise and applying F to it. But we don't want to do that, obviously. And as you can see, every single time F is represented in this algorithm, it's always being multiplied by something to pull it back into a small lower dimensional subspace. But I don't want to evaluate the inside as an n by n matrix, slap F onto it, and then project down. I want to be able to do that without reconstructing U. Because if I reconstruct U, I essentially lose all the benefits of the low rank savings computationally wise, unless I want to go through, and that's just too expensive usually. So how do we evaluate this F? And again, we want to evaluate this F without forming the matrix product, USCSD, or a tensor product in the higher dimensional case. This can usually be done, and in a lot of cases people care about, F is evaluated mode by mode in the tensor context. So with some terms in the middle. So in this case, we're going to say some linear form is inseparable if you can rewrite it as a sum of n terms, capital N terms, of essentially operations on each side of the tensor, each mode of the tensor. Then say I want to evaluate this F of U times D, then I can substitute U in here. Sorry, there's a typo. The transpose should be on the D only. But you can do some associativity and rewrite this as D times B times D, D times B times D, and then A times C times S. And essentially I'm splitting across the components that multiply to give you the full matrix, right? So this is now N by R, and this is now R by R, and I can evaluate those, multiply them together, and never have to build the full N by N matrix. And I can just do this over multiple terms. So you have some amount of terms you have to do this with, and I then can evaluate this very cheaply, because doing it essentially separating the actions over modes. I will say that for the problems people care about, N can be quite large. It's usually dependent on the number of modes in your system, and it can be exponential in that respect.
So sorry, that's capital N that can be quite large?
Yes, depending on your problem, yes.
And large is like millions, or
no. I mean large, like 10 or 15 or something. But
okay.
It does scale, doesn't scale great with dimension.
Got it.
And this is especially in the case if you want to preserve numerical effects like stability, you have to change how you do things in different quadrants, and that changes, that essentially that grows the number of n, unfortunately. But what's nice is you can, in traditional PDE approximation approaches that we're using to reduce this to a semi-discrete ODE, they're usually sparse, the operator matrices. So you can construct this without ever having to build some sort of n squared or m squared system. And this separability carries to nonlinear as long as the nonlinearities of your matrix of your nonlinearities depending on U are separable in the modes as well. So we'll see an example of that happening soon here. Okay. So I wanted to give an example of this dynamical low rank at work now that we actually have some integrators that we can use this with. So a very popular problem for kinetic theory and plasma physics is what's called the Vlasov-Poisson two-stream instability problem. So this is a problem in 2 dimensions. So we're in a matrix case. So we have a physical space and a velocity space, momentum space coordinate. And it's given by this transport operator's transport PDE. Where this is nonlinear because essentially, so for the physics definition, this is essentially transportive velocity. This essentially says that your particles move with respect to the velocity, and this is your acceleration term, where the particles, the change in velocity with respect to some acceleration given by an electromagnetic potential. And this electromagnetic potential is coupled to the distribution using a Poisson problem, essentially. And it's nonlinear, but the nonlinearity is only in the x direction. So I can essentially, this is still separable. You have a v times a derivative in x, and you have an e that depends on u times, but it's only an x times a derivative of v. So you still have this separability that we can exploit. Physicists care about this because there's a class of equilibrium for this solution that are unstable. If you perturb the equilibria ever so slightly, you diverge far away from the equilibrium and get very fine scale behavior in the velocity direction. This is called two-stream instability. I also think people like this problem because it creates pretty pictures, and you'll see the pictures are quite pretty, so people like that. So I do discontinuous Galerkin a lot for the numerical PDE. So I want to apply that technique to discretize the PDE in space, X and V. And this will create a matrix ODE y dot equals f of y, where essentially each term in y, each point in y is a degree of freedom in xv. So you have degrees of freedom in x and degrees of freedom in v. In terms of the separability we talked about before, even though it's the 2D problem, because of stability constraints, this will contain 4 terms. So in this case, y is an n by n matrix with 384 degrees of freedom in each mode. And that's because I'm taking 128 uniform cells and I'm using quadratic polynomials, so times 3. So there's essentially 3 degrees of freedom in every cell in each dimension, each mode. And I'm going to use dynamical low rank approximation with the basis update in Galerkin method, with Runge-Kutta 2 time stepping in each substep. This is just to maintain the stability of the DG method. And we'll use 3 ranks here, rank of 25, so pretty small, a rank of 50, and then a rank of 384, which is full rank in this case. So this would be just doing the problem. Okay. So I'm going to step out this because I have a video. Oop. Okay, can everyone see the video? All right. So so essentially, as I start, we'll see some filamentation develop, and up to this point, kind of each method's behaving equally. As time progresses, the solution will become a little more higher rank to where the plot on the left, the rank 25, cannot keep up. And as you can see, you'll start developing oscillations due to the consistency error, the rank consistency error. Essentially, the solution is too far away from a rank 25 solution, so you receive some oscillations of it trying to give it the closest rank 25 solution possible. The rank 50 solution in the middle there is pretty much identical to the eye test to the full rank solution on the far right. So we're able to.
Sorry, can you clarify this last statement? So the solution is too far from rank 25 solution. If I were to take what you have on the right, and I were to try to find the closest rank 25 solution, would it really be as far as what you have on the left? Like, is it an artifact of the dynamics, or is it an artifact of the complexity of the solution?
It's an artifact of the so the true solution is far away from a rank 25 solution. So there's not enough data in rank 25 to capture the dynamics of this problem given to you. So it's trying its best, and it's not good enough, essentially, on the left, if that answers your question.
Well, I guess my question is, how do you know this?
I mean, essentially, this is, if you crank up the rank as you see the rank 50, you get a much better resolution of dynamics. So it's not
but this is, sorry, it's the question of how you got there, right? I mean, like, is what we're seeing on the left an artifact of how the dynamics has evolved? Like, if I were to forget about all of this and I would try to find the closest point on this,
yes, I would propose that if you tried to find so there's two things, right? So once you are carrying error as a function of time, right? So
Right.
if your solution in terms of dynamical low rank, if you leave the manifold far and then the solution instantly drops to low rank, you do carry that error forward, right? But so in that respect, if you said, okay, I'm going to try to find a rank 25 SVD truncation of this right here, it might be significantly better. In this case, it's not going to be, because the solution does leave far away. But in the case of if your solution did come back to low rank, there is a chance that the dynamical low rank would miss that if you kept it going, because you've created
okay, that answers my question. Yeah, thanks.
Okay, yeah, no problem.
Yes, I think you touched that on the bit. So when we look at the eigenvalues of the system, like when you're looking at the deflection, so after, like, when will it start getting flatter? Like on the full rank 384 system, when you start looking at the eigenvalues, when does it start getting flatter? Like so y in 50, it is able to render, that is, it is looking as good as 384. Right? Like, so when does there is, after what rank, adding more information doesn't matter here in this case? Like, is it like representative of the system, or why the rank 50 is looking closer to 384 and not rank 20?
So it does depend on the system, right? So there's been a lot of work in what are called adaptive rank, where essentially you allow the algorithm to choose the rank for you. Because here I'm just choosing it a priori, so I just chose 3 ranks and ran it, right? So you're gonna see some in the rank 50, you're always gonna see some singular values being very close to 0, essentially, to where these two essentially match.
Okay.
But this is all chosen a priori, right? So I have worked in methods of adapting the rank in time, right? Because essentially you don't want this rank 20. So maybe I should say this better. In the beginning, right here, rank 25 is sufficient to capture the dynamics of the method, right? But as you progress, you'd want to increase your rank sometime around here when you see these effects happen.
Okay. So that's why you're thinking about adaptive rank, like in the earlier in the time system, a lower rank could be better, but as the time increases, you want to look at an adaptive rank system, so that as the time increases, we can go for a higher rank.
Or maybe the opposite effect happened, right? So maybe you, in terms of the physics case right here, you maybe have some higher rank because of electrostatic effects here. But maybe in long time, the collisions take effect eventually, and then you get back down to some sort of equilibrium. So you want to increase your rank, then maybe decrease your rank, right, to capture what you need to capture. Exactly. But yes, there are multiple reasons to want to adapt the rank.
Okay.
Any other questions on this cartoon? So the main point here is to show that, I can take 50 isn't super small. I wouldn't consider this problem low rank per se, but I can take a moderate size rank and get some decent compression on the solution versus involving the dynamics in the ambient space. And to the eye test, these are pretty much equivalent. Okay, so only a few more slides here. So those two are, I would say, the primary integrators that allow you to, avoid the curvature of the manifold and stick with the rank R solution for all time, right? If you would like to break the second category, that is, you can keep your solution. You don't have to maintain rank R. You don't have to maintain rank R, at least within a time step. You can do some other techniques. And for example, one of them's just doing forward Euler on the dynamical low rank system itself. So given essentially forward Euler on the dynamic low rank system where I fix this, there's a typo here, that shouldn't be a dot. I explicitly peg this at time Tn and then take a delta T of it and then add that to UM. And I have a method that now fixes the tangent space and it evolves and you're good. The problem is that this operator right here is rank 2R. So you go from R to 2R. And if you do some sort of SVD truncation of the coefficients, you can go back down to rank R if you want, right? But you're essentially leaving the manifold and coming back. So it's kind of a hybrid between dynamic low rank and the step truncation. But there are advantages to doing this. Here's a paper if you want to look at that. This has been extended to higher order methods as well. You can also take the augmentations of the previous integrators we saw. So essentially there's this method called the augmented bug, where you use the previous basis and the new basis you create in the S step. So you're going from R to 2R in the S step, but you can get some nice conservation properties and you can decrease the error constant in your local truncation error as well. Doing this. But again, this involves going from R to 2R, so you have to do some sort of truncation unless you're ranked to explode exponentially. There's also work for doing higher order integrators. I'll leave these two. I'll just say that there's a very recent paper coming out to extend this bug integrator to second order in time, with padding it with more basis functions you need. And I do also want to say here that fully implicit integrators are still very wide open, and even semi-implicit integrators, it's not well developed. The theory is. I have a couple papers I'm doing on semi-implicit integrators. But the world of fully implicit is still wide open. This is because the manifold is very weird, right? At very high curvature, well posedness is not necessarily a thing. So there's still a lot of work to be done in this field. Most of the analysis done is in this kind of explicit case where you have a Lipschitz constant of your ODE and you use that for your analysis. I heard mentioned that code bases would be nice. There isn't a lot in terms of like GitHub code for dynamical low rank. I will say that there's this repository called Ensign. I was just at a conference last week where I saw this used on a 6D Lasov type problem that we saw before. So if you feel free to look at this code base and see if it fits your needs. But I also want to say that dynamical low rank is a very good reduced order model for people who care about tensors and tensor operations, because it really just uses the machinery that we're kind of doing in this mimics for operations, right? You have tensor times matrix evaluations for the function. You have QR on the factors. You're doing SVD and higher order SVDs on the core tensor if you want to step back down to a rank R system. A lot of this is using machinery that we have. So I think there's a lot of I think this technique is very synergistic with the goals of this mimics, because it uses a lot of the framework that we're trying to do in this research path. I also want to just give a quick mention of some current research trends going on with purely dynamic low rank. So first off, satisfying structural properties. Physicists care about this a lot. As you saw from the CharmNet mimics, they're really caring about this structural preservation. For example, conservation of moments, asymptotic preservation, that you go to the correct asymptotics in some sort of regime. Do they want to preserve this in dynamical low rank? Again, people want to have higher order dynamic low rank in time and try to figure out the minimal amount of basis functions you need to get that. And then lastly, people want fully implicit as well. Again, that's a very, very, very actively researched topic, and it's not been fully settled, but people do want that. And also there's, using dynamic low rank in conjunction with other techniques, right? That's also popular, but that's not a pure dynamic low rank. Okay, so I'm not going to go through all the references, but these are the references used throughout the whole entire section. So if you had something you want to look for, feel free to look at the PDF later and figure out the reference you want. And that's it. So if there are any other questions, thank you.
The example you showed with the 25, 50, and 384, like, was that a MATLAB code or a Python code, or what was that done in?
That was done in MATLAB, yes. Okay.
Would it be possible to share that, or is it proprietary, or I don't know?
I could clean it up and I just kind of hacked it together from what
No need to clean it up. Don't spend any time cleaning it up for me. for us. It's fine if it's atrocious as long as it works.
Yeah, I mean, it's atrocious and it works. But yeah, I mean, it wouldn't be. I have a GitHub that just has this, so I could just add it to there and send it. Sure, I could do that. It's not a problem. But again, I do want to emphasize that, like, it's just tensor operations with an SVD and QRs built in. Like, it's not the most complicated things are assembling these operator matrices, which is the numerics that I do. But besides that, it's just applying matrix gems and QRs and doing it in the right order.
I have a quick question. I was wondering how much error, like how expensive the projection steps are and how much error you can tolerate. For example, like maybe a noisy projection, is that something that you can tolerate, or does it really have to be exact?
No, it's robust to noise. So I have a work on rank adaptivity where we use a randomized SVD to use as an error estimator. And it's pretty robust to that. So I think having approximate projections via some randomized algorithm is perfectly fine for this. The main things are evaluating the Fs properly, right? But if you had some sort of set sampling method that can get you close enough, I don't see how that's gonna. I do not see how that is going to overestimate either the rank error or the consistency error by the time step.
Cool, thank you.
So on that dimension, like roughly what's the breakdown in runtime between evaluating the Fs and the other linear operations, like the other linear algebra involved in this?
The evaluations of the F is the most important, and that's because of the number of and this is where I said the number of terms in this form is where it takes to effect, right? So if you had a lot of terms, then you're spending a lot of time churning through F, because you have to, if you want to keep memory. Now, if you have a higher memory footprint, you can do these in parallel and add them together, right? But if you're doing this sequentially, you essentially evaluate each term and go. A lot of the runtime here is spent on the evaluation. So this is some of these we can talk. There's other advantages, disadvantages to these algorithms. So this bug underwear takes 3 evaluations of F every single time step to do this, right? And some of them only take 2, and that can be important if you care about that. But from my experience, it's evaluating the cost is evaluating the function.
I have a related question. How many ODE steps did you have to do for this problem?
Are you talking about this problem right here? You mean the number of time steps?
Yeah, the example you gave.
This is
Yeah,
like 20,000.
how many steps?
This is
20,000. Yeah, that's quite a lot. Yeah.
Yeah. So this is a disadvantage of all reduced order models. Well, not all, but I would say that, if you want to, the goal in terms of the kinetics is to get very high fidelity solutions, right? So you crank down you crank down the resolution or crank up the resolution, and that induces a time step restriction that's dependent on the resolution, right? So even if I'm in this reduced order model, especially in these areas, when I have these areas where I have high filamentation here in velocity, my basis functions are going to be very oscillatory, maybe in velocity, and I'm still going to have to keep that fine resolution time step restriction. So this is why people care about implicit methods a lot and fully implicit methods. It's like one kind of time step. If I'm creating this large error anyway, maybe from the rank approximation or larger than from the rank approximation, I like to just time step over some of this stuff implicitly if I can, and not have to worry about resolving the CFL, hyperbolic CFL of the problem.
And how did you validate the projected dynamics in the end? It's the error compared to the if you do this in the original manifold. Oh,
so I have not computed this using the equations of motion, if that's what you're asking.
That's right. Yeah.
That would require a way small time step. I mean, you could do some regularization, but like, I've never seen someone use the equations of motion in the past, 15, ever since it was created. Essentially, once once it's projector splitting, no one's used the equations of motion just because I would have to take time steps of, super, super small. It's not worth it. So I have no reference to compare to using the equations of motion, if that's your question.
Stefan, I'm wondering if you have seen applications of this on tensor-based optimization problems, like tensor decomposition, tensor approximation, completion, etc. Writing the optimization as a gradient flow and use this technique to
So I've seen I've seen now this is not in the tensor case, but in the matrix case, people have shown that for these problems, it's almost equivalent to like ALS and stuff, right? In terms of like rank optimization. So I'm pretty sure you could develop an algorithm that uses dynamical low rank in order, if you're looking in terms of the gradient flow, you can use it as essentially treat your dynamical system as a gradient flow to some equilibrium and use dynamical low rank to try to find the equilibrium.
But then you'll need to be able to take large steps, I suppose.
Yes, but you can still, because the delta t is a consistency error, you could do these substeps implicitly in time, right? So you could still do that. And now you're essentially thinking this is just an iterative method to find some local equilibrium.
Yeah. Okay. Thanks.
Thank you, Stefan. I think people are slowly disappearing, so let's stop here and really appreciate it.
Yeah, before hanging up, just wanted to tell everyone, like, next week is IMPP. So book your tickets, register, book your hotel.
If you haven't done those, it's too late. I think at this point.
We'll see you guys next week. Yeah.
I'll be there, even though I have no role other than clapping people.
If you want a different take, you should start thinking about mini symposiums for SciM Mathematics of Data Science, which are due in about a month, I think.
When is it, the actual conference?
It's going to be October something, mid-October in Atlanta.
Nice. It might happen.
It's going to be in Atlanta this year, is it? Okay. I think, okay, we'll think about something. David, yeah.
Thank you, folks. And thank you, Stefan, again, so much. And in 2 weeks, Dimitri will be with us. He's probably already dropped to the next meeting, but I see him all the time. I'll remind him. And he's going to give us a tutorial on persistent homology.